Okay, previously we stopped at drawing a straight line, a tie line. The tie line will help you to find LOS point. And by using the ratio, we can find the percentage of liquid, right, will be total length, and then divided by the solid side. Percentage of solid will be total length divided by the liquid length. So same as this one. Before you okay, then you draw the temperature line, you draw straight, and then in the question you look at what are the percentage of that particular component. So read carefully the caption. So here is 70% of Ag. So 70% is this one. So draw a straight line. This one will be your X, or this one will be your WO. So this two red line is very important when you solve. Please draw this dashed line in the answer in the graph. Later you need to detach it and stapler together with the answer. Okay. Then after that you label LOS. So in this case, L is on this here. L is on the liquid side. O is the one that you want to find. S is the one that on the solid side. Then you go to okay, so you can write the numbers. For example, here you will see 74, you write 74. Here you write you see 64, you write 64. Okay. Then it depends on whether the question asks you percentage or what. WT, this one is WT question with percentage. Okay, so if you look at the sample answer here, you're able to understand how to get 40%. Okay, so percentage of liquid, the total length is 10. Liquid, percentage of liquid, you take the OS or SO length divided by the total length. Total length is 10, OS is 6. Yeah. Okay. I think the answer is wrong on my slides. It should be solid, not liquid. If this 40%, it should be solid. Solid, you take the total length is 10. If you see 40% is this length. 40. Yeah, correct. Here is 4, here is 6. So again, typo error on my slides. It's not solid. It's not liquid, but it's solid. Okay, so if you have no issue on the LOS, you should be able to score at least 12 out of 25. So this one will be half question in the final exam. Okay, now all this graph, we reduce the temperature evenly. Mean we control the dropping of temperature. So that's why you get all this line. Today we look at what happens if you extremely cool down the material. Okay. So it will fall under non-equilibrium cooling or non-equilibrium solidification. Okay. So if you have this kind of microstructure, it means that the temperature is not well controlled, or it was purposely cool down either very slowly or very quickly. Okay. So this is called cold microstructure. Cold microstructure. All right. Now today we'll look at The blue line is what you're familiar with previously. Liquid, solid, and then solid plus liquid in the middle. Okay. Now today we are more interested in the black line. So on the y-axis is your temperature. X-axis is your percentage of copper. Okay. So we'll consider a sample, nickel copper sample or binary system. When we cool down at a very rapid rate, mean cool down very fast. So here, how you know it cool very fast? By the gradient of the line. Huh? So this one a bit slower compared to the black line. Black line, you cool down very fast. Okay, we look at one point to study what happened to the microstructure. So we pick 70% nickel, 30% copper. So here is copper. So as you move to the right is copper percentage. So here 30%. So you draw 30% line here. And we start to see what happened to each of the point. Okay. So this section, I'll show you this one. This section is actually tell you is extract from one of the graph here. It's only flip the side. But this is liquid on the here, solid here. So actually you flip the graph. Okay, you're flipping the graph. Okay, so this section is actually here. This section. It's only you flipping the graph. Okay. So we go back to the diagram. We start to look at point by point. TO means from the early melting temperature, very high temperature, then you drop down to T1. The temperature drop from T0 to T1 means it start to cool down and has a composition of alpha 1. So this is a solid line. This line is a solid line. So after this line all solid, means you step on this one, you start to see solid particles already. Then this one is liquid. Right? So L1 have a composition of solid alpha 1. So upon further rapid, now we look at rapid cooling. Rapid cooling, the black line from T1 to T2, you will see alpha, 2. Alpha, 2, and the normal cooling will be alpha 2. So additional layer of composition, alpha 2, will be formed without changing much in the composition of solid or primary solidificate. So when you drop now from temperature from 1455, you drop to T1, which is below 1455, you start to form alpha 1. So we just simplify the diagram with one sphere, alpha 1. Then as you drop further, you start to see alpha 2. Start to see alpha. I think in my diagram, in the rapid cooling, I should put alpha comma. So this one, I think without the alpha comma lah. Okay. So if you normal cooling, yes, normal cooling is alpha 2, but rapid cooling, you'll see alpha comma. So how you draw the diagram? In T2 location, you draw a sphere, then you are showing this diagram. You draw circle, you write alpha 1, draw another circle, you go to the space there, you write alpha 2. You got alpha 1, alpha 2 lah. It depends on the location. It depends on the location. For example, T2, he asks you this point or this point. It's still the same. Alpha. If this one, I draw the blue line. Blue line at the back line. This is also important. We'll ask you in the test lah. So what are the microstructure will form if you rapid cool and normal cool? So I draw the blue one. So at T1, what should you draw in your diagram? Okay, at T0, you no need to draw anything. under microscope, if you put that under microscope, you will see liquid. You just write liquid. Then you drop temperature to T1, you start to form alpha. Alpha 1. Okay, you start to draw alpha 1. Alpha 1. You don't need to draw 3 as long as you draw 2 or 1 also correct. Okay. Now I draw alpha 3. Sorry, T3. T2. Okay, T2, you start to see alpha 2, right? So you draw one big circle under like a microscope lens. Then you copy your alpha 2, alpha 1, and you draw another layer outside. This is alpha 2. This is at T2. So what happens if you're having a rapid cooling? Rapid cooling, I use still intersect there. So you're still seeing liquid TO at TO this point. TO or TO here. Then T1, you start to see a little bit of, you can say here got alpha 1. Or you can, because this graph doesn't label anything, comma there lah. So this one rapid cooling. Okay, rapid cooling. T2 at T1, you draw alpha 1, comma. Or if the graph like what you see on here, you just draw alpha 1 also correct lah. See alpha 2 already. Okay, same, you draw 2 layer, alpha 1, comma, alpha 2, comma. Okay, and so on. The rest is just self-introduction about what's going to happen. It will snowball the size. So the overall composition at T2 lies somewhere between alpha 1 and alpha 2 and will be defined as alpha 2, comma. Okay. So here, since the tie line of L2 to L2 here, the tie line, since the tie line of rapid cooling is longer than the normal cooling, alpha 2, L1, what's the same mean? What does the tie line tell you if you have two different tie line? One is rapid cooling, one is the normal cooling. Normal cooling got shorter. Right? Shorter. What does it mean? From here, what does it mean? Okay. So you normal what? You label what? You label L. O is somewhere here. S is here. So L, O, S. So if you calculate the same composition, let's pick one composition. So you know that this side will be the same length, right? Then another side will be longer and shorter. So if you calculate percentage of solid, percent solid is this side. Okay. Percentage solid will be the same. LO and, sorry, not LO. LS and LO. Percentage of liquid will be a bit longer, LS also, and LSO. So you compare rapid cooling, you have more liquid compared to the normal cooling. I mean, if you rapid cooling, it's like you put water inside fridge, and then you cool it down very fast. Sometimes inside ice cube, they got water one. Got water inside. Same as these metal things. Same as these metal things. So I'm going to show you the other slides. So there will be more liquid compared to the normal equilibrium condition. So if you cool it down very fast, it's called non-equilibrium state. If you cool it in a normal condition, it's called equilibrium state. So just want to highlight, you have more liquid percentage in a rapid cooling. So solidification has been delayed at the temperature by rapid cooling. If you cool it down, solidification process have been delayed. The time to solidify have been delayed, mean longer time to solidate. Okay. So as the temperature lowered from T3 to T7, as you can see here, the length of the gap become longer and longer. Okay. So I just show you at T6. At T6 here, the solid freezing has less copper than original composition of alloy, which is 30%. Okay, at T6 here, the percentage of solid, okay, at T6, you extend this one, you drop down, the percentage that solidified, the copper percentage was less than 30%. Okay. At temperature T7, the average composition of alloy is 30%. So at T7 only it reached the normal 30%. If in the normal cool down, you already reach 30% roughly at T5. But in rapid cooling, your percentage of copper only reach 30% when you cool it further. Then only reach 30%. Okay. This is what rapid cooling will do to your object. Okay. Now on the engineering side, it means you already learn the effect of because if you have liquid, then you'll form something like this on the casting. So what they do in the process, the ingot or the casting are heated to an elevated temperature to accelerate the solid state fusion. Means in normal case, they want to do manufacturing process. Normally they will warm the ingot first. They will elevate the temperature first, right? This process in the industry is called homogenization. Right? Okay, back to the homogenization or homogenizing the heat treatment must be carried out at a temperature that is lower than the lowest melting solid in the cast iron, or else melting will temperature will occur. So this one is just say that if you do this process, the temperature is below melting temperature in the layman term. Okay. So in this case, if you want to get 30% of copper, what you do, you use T7 to do the cooling. Means you heat the the sample at T7 before you do the other process. Okay. So if you have more more temperature, it's overheat, local melting and liquidation might take place. Yes. No, you okay. This one, if like you want to process, you mix between copper and nickel, a solution, then you want to reach a 30% copper all the time. So what you do, you heat up this block to T7. Then only maybe after that you either heat it up or heat it down, so that you always start from 30% if you want to control at 30%. So that like this. So when you heat up like T7, what you do, even is rapid cooling, you start with 30%. If you increase the temperature from T7 to T5, you still reach 30%. So inside here, if you already, let's say you super cool it and then you see the liquid here, there's a liquid there. Right? So if you super cool it, you'll get liquid form. If you don't want to get this scenario, what you do, so when you cool it down, I mean not cool it down, when you want to do manufacturing or this, you control at the block there at T7, lower temperature than melting temperature. What do I mean? Okay, so the blue line is a normal operation. So blue line, if you want to get 30%, you want to get 30% copper, what is the temperature that you start seeing melting? Is T5. Right? So in the normal copper block, you want to see 30% copper in the process, you need to heat the solution or the metals at the T5 point so that you get 30% copper. But you don't want to disturb the process. So in the metal, what you do, you heat it up, you preheat first before you further heat or you want to melt it or something. This temperature, this T7 actually for if you want to do cold working, hot working, you want to hammer it, you want to make it more harder, then you control at, like for example, in this case, you control at T7. Understand? Okay, if you don't understand, it's still okay. As long as you're able to draw this diagram, it's fine. Yeah. So this is just a schematic diagram. Schematic diagram. This is just additional notes on the trade line and all this. Okay, so here is L, this one is L, this one is O, this one is S, LOS. So to find the percentage of solid, you take this part. To find the percentage of liquid, you find this part. Okay, this is just a recap on finding the equilibrium. Okay, now this is a normal cooling. I want to show you what happened in the very non-equilibrium cases. So on the left is normal cooling. Okay. On the top is liquid section. On the bottom is solid section. Let's say the question asks you to draw the bubble diagram at composition of, let's say this is 35% nickel. So what you do, you draw a line from 35%. Then you'll see in the question, we will label A, B, C, D, E point for you to draw the bubble. Okay. So on the point here, 1300 degree, you only see liquid. So what you do in the bubble, you can either write liquid or you write capital L. You just copy what you see on the diagram. Then you write bracket 35% nickel. Okay, this one makes sense, huh? Then after that, you drop the temperature down from 35%. You drop down, it touch the first line. First line is what? First line is start the solidification process already. Means you start to see chicken pox inside the liquid. So here you draw a line here, or in your answer you just draw a bubble, then you label the B point, then you start to see chicken pox there already. You draw a dot like that. Then you label the empty space is liquid. You write L bracket 35% nickel. Then what is the chicken pox? You need to tell the examiner what is the dot in your diagram. You label this one is what? Is alpha nickel. You know this one is alpha nickel, but you don't know how many percent is nickel, right? This is solid, right? This is solid. So how you know is 46% nickel? You extend this line, this dot, extend this line to the right. Because as here, at this temperature here, at point B temperature, T1, the particle or the chicken pox form is this solid percentage. This side is solid, right? So you drop down, you get 46. So what is the challenging part is you writing the percentage of the chicken pox. Yeah. So the first diagram, alpha bracket 46% nickel. Okay, all right, then we further drop, we further drop the diagram. B no issue. Now you go to C issue. C you start to see LOS exercise already. This is L, this is O, this is S. So at C point, your C point is alpha and liquid. So you draw circle and then you label the empty space is liquid. Liquid is 30. Okay, liquid, you need to bracket how many percent? Here got liquid and solid. How many percent of liquid? You from this dot, you expand to the left, you get liquid. Expand to the right, you get percentage of solid. Understand? So this one, L bracket 32 nickel. How you get 32? Liquid. You extend to the left, you touch the liquid region. Extend down, you get 32%. C point, extend to the right, you get percentage of solid. You extend down, you get 43%. So your alpha, although it's a solid, but solid have 43% of nickel. Understand? The percentage change as you drop further and further. Okay. What point? In this case, we focus on nickel. We focus on nickel. Of course, you can write percentage of copper if you want, but we don't want to confuse you. Okay, so this one is just focus on the main ingredient because we know that total is 100%. So you don't need to write another, although this one, you know that it's a binary system. You don't need to worry about another element. You just focus on the caption. Let's say this caption is nickel, then you focus on the nickel component. So another component is just you take 100% minus that one. You get this one. Okay. So of course, the more complete illustration here is like, for example, alpha, 46% nickel will come with 54% copper, for example. If this one copper, I'm not sure. Right. So the more complete illustration is this, but it's sufficient. You only like the nickel component. Okay. Any question on the C point? Any one of you have question on the percentage? No, right? Okay, then you drop to D. D point already touched the solid point already. So already start the D is just D point is still have liquid just a little bit of liquid. After pass this dot, then all liquid all solid To the left you still seeing liquid So here D point, that's what you see a yellow color area. L 24% nickel. So drop down, you get 34. And alpha here is 35%. You drop down, you get 35%. And you know that this remember when you draw this one, the chicken pox, please grow your chicken pox. Grow the grain size, the solid particles. Okay. Then E point, of course, E point is solid. So you know that this one is all alpha. So in your circle there, you just need to draw the boundaries, the grain boundaries. Then you write alpha, alpha, alpha. Then, of course, so this is a normal cooling process. If you understand this one, we move to the neighbor on the right. Then you make comparison. What is actually happen when you rapid cool it? Yeah. Okay. So same. Now we refer to the same point. 35% reference point. 35% nickel. Nickel. We start from same point. 1,300 point. There's a comma there just to represent we are looking at rapid cooling or non-equilibrium cases. So here all liquid, so you write liquid 35% nickel. Then you touch this point already. When you touch this point, you start to see chicken pox. How you know percentage of liquid or solid? So this one you still seeing liquid and a little bit of solid. So here liquid 35%. Another side is this point, you touch down, you get 46%. So alpha 46% of nickel. Then as you drop down, if you drop down to C comma, this dashed line is rapid cooling. This dashed line is rapid cooling. So C point, you need to extend your line to the dash line. So at C point, you have liquid. So liquid will be 29%, but the solid part will increase to 42%. So when you write, you draw circle, you write dash line, you drop down, you get 42%. 40. Okay. This one, the one that you see on here is on this point that is referring to, let's see, 46. Okay. Rapid cooling one, it will have a join of the previous one. Rapid cooling one, it will have another layer. It will carry forward the previous one. But the normal cooling one don't have. You see the left, right? You see this one got 2 layers. So inside one got the previous one, 46%. And then outside one got 40% here. For this dot here, or this dot here. Although here he tell you got 42% nickel, but at this point, if you look at microscope, it will just cover, you have two layer of alpha and alpha 1 and alpha 2 here, right? So you have 46 and 40%. Although here is 42%. So in the diagram, there is we do not include 42%. Okay. Now you go drop further at D point. You repeat the same, repeat point. Although rapid cooling here, you reach 38% of nickel. But when you reach this point, D point, you see how they draw? Liquid still there. Liquid you still read from the left hand side, 42% drop down. But the way you draw it is become more and more layer. So day one you got 3 layer already. This one 2 layer, this one 3 layer. And the percentage is always copy the previous one. So inner layer 46, second layer will be 40%, third layer will be 35%. Then you drop further, the bubble keep repeating and have more and more layer. So for example, this point, D, and then you go to expand to this dot here. Okay, this dot. This dot here is alpha liquid, and then the another side is liquid already. But here you see there's an extend line here. Extend line here. So extend line here means there's more liquid component, more liquid percentage. Because if you take LOS and LOS analysis, they're more liquid. So here you have liquid will be 22%. This one I already explained. Then you drop to E point. E point here, you have liquid 21%. Then 40, 46, 35. Outside one will be 35 if refer to this point. 35%. And then the liquid, the solid side is you fill up, bro. The fill up. Just the 31% will be the most outside layer. So normal cooling and rapid cooling, the differences is if you cut the particles out, you will see layer by layer. Okay. So it's important, you know how to draw all these bubble. It's important. So one bubble might cost you 2 to 3 marks. So it easily can be half question. Half question. Sometimes like in test 2, it can be one question alone. Okay. This one is just to show you a new graph. Previously, what you see is the ellipse shape, right? Now it's a new shape. So from here, can you see triple point? You still remember what is triple point? Triple point means got 3 faces or 3 different components. So as long as there are 3 intersection line, there is a triple point. This is a triple point. This triple point got alpha, alpha plus liquid, alpha plus beta. This one also, this one is more than, this one is, this one got 1, 2, 3, 4. This one more than 4. Okay, this one is triple point. This one is beta liquid, beta, and solid. Okay. Now, for the graph that you see here, we start to learn new terms for metals. We go it slowly. We go it slowly. So this is the lead tin equilibrium diagram. Okay. So this tin got 2 sides in solid, 2 different solid. Left hand side is alpha solid. Right hand side is beta solid. This one is SN is tin. SN is tin. So on the left-hand side, you will see alpha solid. On the right-hand side, you will see beta solid. Okay, there's one point called eutectic. There's one point, new term for today. Eutectic. There's a eutectic reaction on the graph. How you know that is a eutectic? On the graph, when you see two different solids, then there's a straight line connecting the alpha and connecting the beta. You draw a line. This is a eutectic line. So eutectic point is somewhere that is liquid and solid are formed. So this is a liquid region. It's a liquid region. This is a alpha and beta mixture. This line. This side is alpha. This side is beta. So when there's a mixture of alpha beta point, that is called eutectic point. Okay, eutectic means combination of two solids. It means you can find two solids at the same time. Yeah. So this is the first term for today, eutectic. Yeah. And on the graph later, you'll see different kind of graph, different kind of shape. It will ask you to find eutectic point. So the first step of finding eutectic means two solid. Most of the time they are alpha beta. Sometimes it's alpha gamma or gamma beta. Sometimes it depends. Then you find intersection point of alpha beta. So in this case, you find where is the point where alpha exists, beta exists. You draw a straight line or you follow the line connecting the alpha beta. Then somewhere along the line, you will see one type of the alpha will form. On the line, you will see one type of the alpha solid will form. So the combination of alpha beta, you will reach one point. That point is called eutectic. Okay. So this point form at one particular temperature. In this case, you follow the line, you draw the straight line, you will reach at one temperature, 183 degree. So this usually will be very popular in tests. We will ask you to find the eutectic temperature. Usually just use your ruler, go and find any straight line, join two solid, draw to the left, you get the temperature. And then also, it will ask you to find at what percentage of that component. So you draw eutectic, you reach the intersection point, then you draw one line, you read the reading from the bottom, in this case, about 62%. Okay. So here you have 61%, 62% SN, and at eutectic point, alpha is at this point, you have two solid. At this point, you have two solid. One is alpha, one is beta. So how many percent of alpha you read from the graph? Extend from here, reach alpha, drop down, you get 19.2% alpha. Move to the right, drop down, you get 97.5% SN. So SN got two form, one is alpha form, one is beta form. Okay, percentage of each other is also important. This is a alpha form. Beta is here. So here this region is alpha plus beta. So as long as this you cross this line, you start to see beta. Okay, you cross this line because this region is alpha plus beta. This one only all 100% alpha. So you cross this line, you start to see chickenpox beta. Same is here. Beta, you cross these boundaries, you start to see chickenpox alpha after you cross this point. Okay. Which one? This one. Or this one. This one you see on the graph. Blue line you are seen in the question. The blue line will be given, but only you need to identify which line is called. I will remove all this. I will remove this eutectic point. I'll remove this one. I'll remove this arrow. I'll remove all this bubble lah. I'll remove this temperature also lah. So you should know what line is eutectic line, and then where is eutectic point. Then from the eutectic point, you should be able to tell how many percent alpha, how many percent beta. Okay, so this is a new type of graph. Compare a bit different from the previous one. The previous ellipse one is only one type of solid, right? Liquid, solid, and liquid plus solid, the previous one. But this one, you will see on the graph, you'll see two types of solid on the same graph. Okay, so eutectic only appeared on on the graph phase diagram that show you two different solid. Okay. Okay, we go straight a little bit more. Okay. This one is just a highlight before we move to the next slide to make sure you understand the meaning of all this line. What does it mean? What happened if you cross the line? What happened? Right. So for example, if you cross alpha to alpha plus liquid. So these are all alpha solid line, solid region. You cross the line, or as you walk on the line, start to have liquid already. Okay, start to have liquid. Now you might ask, what kind of liquid you have? The liquid can be alpha liquid, right? It can be beta liquid. Is unable to identify, but it's in liquid form. Because liquid is able to move around, so you unable like to quantify how many percent of alpha. So we just straight away write the form of that state. But we can only identify solid under microscope and under the testing material equipment. We get solid one, we can pick and then we put inside the testing machine. You can identify this is alpha. But liquid cannot. Liquid is still running here and there. It's very hard. Okay. Another one is sometimes the point of this one is called terminal solid solution. This alpha, beta, they are called terminal. So you have two terminal, alpha terminal and beta terminal. Okay. The alpha phase is the lead-rich solid solution. Are you able to see this statement? In alpha phase, is the lead-free, lead-rich. Lead means PB rich. This one, you have almost 100%, or the least one is 80% of PB, alpha region. So alpha phase is another statement is called alpha phase. They are lead-rich solid solution because PB is very high. Okay, can dissolve in solid solution a maximum of 19.2% of SN at this temperature. So alpha phase, it can dissolve the maximum weight percentage of 19.2 SN at 183 degrees C. It can dissolve 19.2% of tin at this temperature. Can I? Understand? Okay, if you understand, I ask you, in beta phase, what is the maximum WT of Sn? What is the maximum WT Sn at 183 degrees C if it's beta phase? See, 97.5. If you want to get beta phase, you heat the solution or you cool down the solution to 183 degrees C. It will reach here. And the percentage of Sn you can solve, you can dissolve is 97.5% to get beta. Okay. The rest is just graph reading the graph. So beta phase is thin rich solid solution. So you should be able to describe whether it's a thin rich or lead rich solid solution. So left hand side because you have a loss of PB, so that's called PB rich. Right hand side because you have a loss of Sn, so it is a thin rich solid solution. Okay, so can maximum dissolve 2.5% of PB at this temperature. So this is everything from the graph lah. So if you understand this statement, then you're okay. If you understand this statement, then you are okay. Yeah. So the question can just give you one graph and then ask you so many things by referring to the graph. Then you describe whether it's what rich solid solution, depending on the element that you see. Okay. Then we focus into the graph. So this one will be on the left-hand side of the graph. We focus on here. We crop it out. We enlarge it. Okay. So this is just, again, is a schematic diagram. And we start from concentration number 1. We pick anywhere that just beside this red color curve here. We pick C1, then you draw one line. Then it's just to test whether you know how to draw the bubble lah. Okay. Now again, if you see the blue line means they are normally cool down. So there's no layer things. If you see layer and layer, then that one is super cool or you cool it down very fast. Here, you only see either liquid, like for example, this region is liquid. Point A, you just write L, and how many percent of that particular component. So this one, because it's C1, so you just copy this number, bracket C1 WT SN, because this is a SN graph. This is a SN graph, so you write SN. Then you drop to B. B already passed liquid and it go into alpha already. You see this dot? This region is alpha. So your chicken pox is alpha, not beta. It's important you label the correct name. Beta is another side. This is alpha. Okay, so you drop further temperature, drop to C. This here already solid already. All solid 100%. No empty space. So you draw like a green boundaries and then you write alpha, alpha, alpha. Then how many percent? Copy the percentage on the ground. So here is C1 percentage SN. Okay. So all the dot also same until here also solid. So what happens if I shift the line a little bit to the left or to the right? Let's say the question I ask you this one. I ask you 10%. Are you able to draw? Say I extend 10%. 10% SN. So same, I label this one is A. I label here is B. I label here is C. I label here D. Are you able to draw? So A, what do you see? What do you see? Liquid. But if you just write L, you don't get full mark. You need to tell me what is this liquid have. So 10% WT SN. If you write L, 50% marks of this one, if this one 2 mark, you only get 1 mark. But normally, if one diagram, I will give until 3 marks. So 3 mark, if you only write L, then 1 mark. Okay. B is what? Alpha. But you need to write how many, in this one, this one you should able to write but this one you can extend to left right One drop down, this one drop down. So you have liquid and alpha. So alpha will be, maybe I just put 5. So here you got 5% SN bracket. Liquid will be 18 or 19, 18% SN. Okay. Liquid liquid. Okay. Okay. So drop to C. C is all alpha. So alpha how many percent? 10%. 10% SN. D. D. You got alpha, you got beta. Both are solid. Again, you need to extend to the left, right. That one, I don't know. Okay, so this one, drop down maybe 3. And the side, you need to read from the bigger graph. Okay, so here, alpha will be 3% SN. Beta, you read for another graph, another side of the line. Okay, yes. Thing will be bigger compared to alpha. No, beta is smaller because it's moving towards alpha zone already. So it will form alpha first, then only form beta. So beta will be smaller portion compared to alpha. It depends on the region. Again, this is normal cooling or equilibrium cooling, so no layer and layer. If it's rapid cooling, then only see layer and layer. Okay. Okay, so if you understand, you're almost done for phase diagram. Okay, this one will be what I draw just now. If you shift a little bit, what do you see and all this? Okay. Okay. Another one, still the same. There is a specific composition known as eutectic composition that freezes at a lower temperature than other composition. There's a specific alloy composition known as eutectic composition that freeze at a lower temperature than other composition. So the lowest temperature which the liquid phase can exist when cooled slowly is called eutectic temperature. So in PV system, what do you think is the temperature? If you read all these statements, what is the temperature? You know eutectic line, right? So it asks you eutectic temperature. There's only one eutectic temperature there, which is 183 degree. Okay. Okay. So we call eutectic point, eutectic point. So eutectic point is the point where alpha beta form, and that is the lowest temperature it can go. Lowest temperature of what? Is the lowest temperature that freeze at lower temperature compared to other composition. So as you can see here, you see liquid, right? What is the lowest liquid that you can see on the graph? If you drop from top to bottom, is this temperature. Right, this line also, liquid come to here, the rest is solid already. Here, yes, you see liquid, but also form the liquid at this temperature, 183. The lowest temperature that you can go. Right? So it's called eutectic temperature. Okay, so again, try to understand the line. What does it mean? Because we will change to other element, but you see the same similar behavior. Okay. Okay. So this one is another one is just another illustration. So if you have, you know that this one is 61.3 is your eutectic composition. So schematic representation of equilibrium microstructure. So this is the word that we will use to ask you to draw the bubble diagram. It's called equilibrium microstructure. It's the bubble, means we want you to draw the bubble things. You won't see bubble in the word bubble in the question. Because it's not professional. So we will use this word to ask you to draw the bubble. Okay, equilibrium microstructure. Okay, another one, eutectic already done. Eutectic done. Eutectic temperature. Okay, now then we need to learn what is eutectic reaction. It means chemical reaction. Input, process, output. Input, process, output. Input is what? Liquid. You drop from liquid form and cool down. You are cooling, you drop the temperature. Cool down at what temperature? The temperature is called eutectic temperature. So you refer to the graph. If this one, the graph is 183, you write 183 here. Okay, or you want to write eutectic temperature also can. Equal to output. What is the output? Alpha and beta is what you see in the eutectic reaction. So important, this one is a general equation to get eutectic reaction. We have about 7 to 8 kind of reaction. This is the first one. This is the first one, called eutectic reaction. Okay. So during eutectic reaction, 3 phases coexist and are in equilibrium. What does it mean? If you look at this point, eutectic point, there are three things you can see. You can see alpha, you can see beta, you can see liquid. Okay. So you see liquid, alpha, beta. Liquid to 2 solid. That is eutectic process. Yeah. Okay. Okay. So the rest, this is the Gibbs rules. If you find the Gibbs rules at this point. P minus F plus C plus 2, because this is the pressure is constant. Pressure constant. If you don't see constant, you don't see pressure, means the pressure constant, use C plus 1. Use C plus 1. At the end, you get no freedom at this point. Okay. Thermal arrest. So this is called thermal arrest. Thermal arrest. Okay, you have this straight line is called thermal arrest, but I can split into different things to ask you. Okay, thermal arrest. Or sometimes the question asks you, given a graph, after you identify the eutectic point, it will ask you, identify where is the thermal arrest happen. Label on your graph using A and B, capital A, capital B. Go to the graph, label A. Here you label A. Go to here, label B. Line connecting A, B is the thermal arrest. Okay, something like this. The rest is just reading from graph, slow cooling, eutectic composition. So let's say you cool down from 200 degrees C. So after the temperature above 183, you see liquid. Then you reach 183, eutectic reaction happen. So again, you write the eutectic reaction. Liquid become too solid. You transform the equation just now, put in a few data. What do you see? You see liquid with how many percent of SN, bracket log. So this line is 61.9% SN. Okay. Then to alpha beta. Alpha beta. How you know 19.2? Again, one extend to the left, one extend to the right. Okay, at this point, how many percent alpha? Read from here. How many percent beta? Read from here. One on the left, one on the right. Okay, so this is the eutectic reaction that we expect. If we give you one straight line on the graph, we will give you alloy 1. You explain what actually happened from point number 1, number 2, number 3, number 4, for example. Then actually you want, usually the first part of the question will ask you eutectic reaction. Then we expect you to write this reaction. Okay. Okay. So here, upon cooling from 183 to room temperature, there's a decrease in solubility of solute in the alpha and beta solid solution. So here, so this is called Solver's line. Solver's line means solubility. The solute. Solute mean solute means alien atoms. In this case, you only have alpha or beta. So if you touch this line, means beta can solute in alpha is become smaller and smaller. Less and less beta can dissolve into alpha. Okay, same with this one. This one is less and less alpha you can dissolve into beta. Okay. So solid solubility of the solid element is called Solver's line. Okay. Since diffusion is slow at lower temperature, this process does not normally reach equilibrium. This here, from here to here, do not reach equilibrium. So the solid solution of alpha beta can still be distinguished at room temperature as shown in the microstructure. So if you are slowly cool down, you can still see the differences between alpha beta. For example, this diagram. Okay. Just now we identified eutectic point. You draw a line. When you draw a line, you have left hand side, right hand side. The one to the right is called hypo. The one to the left is called hyper. So, sorry, to the right is hyper, to the left is hypo. Okay, left hand side is called hyper eutectic. Right hand side is called hypo eutectic. Okay, hyper, hypo. Yeah, here we focus on composition. Composition. Composition means percentage of Sn. To the right means hypoeutatic. To the right means hypereutatic. Hypo, huh? Okay. Now we start to look at another line. Alloy 2, 40% Sn, 60% Pb. Alloy 2, solid liquid state, it dropped down from 300 degrees C to room temperature. So let's see the microstructure, how it goes. So at 300 degrees C, it's still liquid. Okay, still liquid. So if you extend to here, it will remain a liquid until it reach this line, liquidus line, at 245 around there. Solid solution contain 12%. Sn will begin to precipitate. 12%. This is alpha. Okay, so 12% Sn alpha will start to precipitate if we drop the temperature. Beta is another side. Beta is another side. Okay. First solid form at this type is called primary or pro-eutectic alpha. So the first dot of alpha is called pro-eutectic or primary alpha. The first dot here. So the question usually like to ask something like, when will be the pro-eutectic alpha appear? If you drop from alloy 2 line, where does it happen? So you draw to the left, you draw this line, B point, you touch the liquidus line, go into alpha plus liquid line, draw to the left, you will get one temperature. So tell the temperature where does the first pro-eutectic alpha appear. So here will be roughly 240 something. Okay. Then the percentage of that solid alpha is how many percent? Okay, so this is what I draw on the graph by the green line. Okay, so just now we learned a few things: eutectic, hyper, pro-eutectic, or primary, not primary, primary alpha. Now we go into BCD point. So as you drop into alpha plus liquid region, there are two phrases, alpha plus alpha. Okay. So composition of alpha follows solidus line, this one, varies from this one, from B is here, 12%, to drop to this line will be 19.2%. Okay, each one got different temperature. Here is about 245. Then this point is 185, 183. Okay. Again, the skill is just reading the graph. You as long as you understand what the line means, you can solve lah. Nothing complex here. Same with the rest same with the rest. Liquid phase, it asks you solid phase, so and so. Asks you liquid phase, as so and so. Liquid phase, you read the liquid line. B liquid percentage is here, 40%. If you drop until D, you read the eutectic line, or just above the eutectic line, drop down, you get 60 something percent. Okay, this is a liquid line. This is a solid line. Okay. Okay, eutectic reaction again, you've seen before. So after eutectic, it become pro-eutectic alpha and eutectic mixture of alpha. Further cooling from here to here lowers the tin content and the lead content. Okay, the rest is just show you how to draw the equilibrium microstructure. So if I draw a line, let's say 40%, on the top you should know how to write how to write liquid. Then here is alpha liquid with chicken pox. Then this one is just above the eutectic. The size just get bigger. You should able to know how to get 18.3. Liquid also, how you should know how to get 61.9% at this point. You just extend to the left, right, you get the percentage. Then after eutectic line, you will get solid. So here is the one. You will get primary alpha in sphere. Then there is a beta. You have primary alpha, then you have eutectic alpha and beta. Okay, so eutectic alpha and beta, so in this straight line. This straight line is called eutectic structure. Yeah. This is just now is tin, PB and SN. Just a recap, whether you understand or not. This is another component. This is AG and CU, but the graph is AG. AG is silver. But again, if you don't understand the chemical word, don't worry, the question will tell you one. Referring to phase diagram of what? Okay. On this graph, are you able to identify eutectic line? Where's eutectic line? Straight line, here to here. BG. Where's eutectic point? E. Okay. Where's the temperature of eutectic happen? Or eutectic temperature? What is the eutectic temperature? Here lah. About 750 lah. About there lah. Or 700, maybe 780, maybe. Okay, as long as you understand. So, are you able to write the eutectic equation for this phase diagram? If yes, then okay. Where is the first pro-eutectic alpha happen? Are you able to find? If I give you the, you drop from 40%, let's say I pick this line. 40. Okay, above one is atomic percentage. Huh? Above one is atomic percentage. Below one is WT. So we let's say I give you X percentage. Where is the first pro-eutectic or primary alpha start to form? What is the temperature? What is the temperature? Where is the first pro-eutectic happen? Where? Yeah, this is the answer. If given you this one, huh? Okay. If the question didn't give you percentage, it didn't give you the X, based on this graph, where is the pro-eutectic alpha start to form? Pro-eutectic alpha start to form if you see this graph. Where? Where? A, yeah? A point, yeah? Then it asks you pro-eutectic beta start to form F point. And so on. So this is another diagram, PBSN. You should be able to see where is a eutectic point, where is a pro-eutectic, where is a hyper. Okay, so you draw a line here, 71.9%. More than 71.9% is called what? Hyper or hypo? It's a hypo, huh? This one hyper, huh? Correct. Hyper, huh? Hypo, huh? Okay. So this one same. And they have a different orientation of alpha and beta. It depends on how you control it. So some they form like laminate one. Some they form like a rod one. Some they form like seeds like that. Some they form like a small fiber like that. Okay. So eutectic structure, it depends on how you control the process. We don't go deep into the chemical process or how you control it. But as long as you know, the A is called lamina, B is called rod type. This is a globular. This is a circular, acicular. Huh? But I won't test you this one. Just let you know there's a form of eutectic structure. Okay, so this under lamina, under microscope, it will look like this. Okay, so example 4, I take as a homework, right? Homework. But before you go back, you look at the question, see you able to know how to answer. Okay, you're given the graph. Make phrase analysis. Following point, for example, at the eutectic composition just below eutectic pressure. I think this one I need to show you. I didn't cover in the lecture just now. Okay, the step is always standard, like SOP. Just now, he asked A, I do A for you, the rest you see. So A, eutectic composition. From here, you know where's eutectic already. Here. So what you do? You add eutectic composition, you need to write at eutectic composition how many percent of SN just below 183. Just below 183 means alpha, beta already. Means solid, there's a solid there. So you write the format, the format you write phrase present. What do you see? Alpha, beta. You don't know how to spell this one, never mind, as long as you copy alpha symbol and beta symbol. Okay. Composition, the first one is phrase, second one is composition. Composition is 19.2% SN bracket alpha. Means you read the left point. Beta is right hand side point. Okay. The third information, amount of phrases. Amount of phrases, you use LOS analysis. Okay, LOS analysis, how many alpha? You take alpha is this side. It's like solid liquid. Alpha is on that side, right? So you are taking this section, total length, and this section. Beta is another side. Take total length and this side. Yeah, it's the same concept as the LOS. The answer is 45.5 WT% and 54.5 WT%. Okay, so these are the format that you follow, you should be able to do. If the question asks you to do phrase analysis. Phrase analysis means we expect to see you write phrase present, composition of phrases, amount of phrases. Then you do accordingly lah. Left hand side is the first component, right hand side is the another component. You just draw a line lah. Okay, this one. Again, you copy this green color line and you see what happened. So B, point C is here at 40% SN 230 degrees C. Phrase present is what? Phrase present. Phrase present will be liquid and alpha. Here, this point. Liquid alpha, you write off. Two phrases, liquid and alpha. Composition will be how many percent alpha, liquid, how many percent alpha? Read from there lah. Read from this point. This is alpha. This is liquid. Okay. The rest is LOS analysis. How many percent liquid? This is the total length. 48 and 15. Total length. This is the center point. So he asks you about liquid. Liquid is this side. So you take this length for liquid. Then you take this length for solid. Okay. The rest, homework, go and see. This is a bit tricky lah. This is plus means above, just above. Just above means you need to carefully draw the line. Just a little bit above the 183, which is the D point here. The rest you read. Then another one, D point is not D point, is point E here. So point E here, you need to shift your purple color line a little bit lower. The same process. Okay. Wrong, the wrong answer here. It should be alpha beta, not liquid alpha. Okay. Example 5, your homework. Okay, next lecture, we look at perithetic and other new terms. Okay, we stop here. Your lab report for engineering material is week 12, Friday. Friday,